Hello, my name is Ishita Nargis. I'm doing a teaching demonstration. The topic of my teaching demonstration is dynamic programming. So here is the plan of my talk. At first, I will give some motivation why we should learn dynamic programming technique, and then I will describe some characteristics of problems that can be solved using dynamic programming technique, and then I will go into detail for one particular problem, the rod cutting problem. I'll describe the problem, define the problem, and then first I'll describe the recursive algorithm. Then there I'll show two dynamic programming algorithm. One is top down and the other one is bottom up, and then I will describe how to construct the solution, and finally I'll describe how to prove a particular property of problems that can be solved using dynamic programming. So dynamic programming is both a mathematical optimization method and an algorithmic paradigm. It was developed by Richard Bellman in the 1950s. In both situations, it refers to simplifying a complicated problem by breaking it down into smaller or simpler subproblems in a recursive way. It is an algorithmic paradigm. That means dynamic programming is a technique for designing algorithms. It is not a specific algorithm. It was developed back in the day when programming meant use the tabular method. That means saving solutions in a table and retrieving solutions from tables like linear programming. It does not refer to computer programming. So next I will describe why we should study dynamic programming technique. There are certain types of problems called optimization problems. For those, dynamic programming is widely used technique, and then I'll describe what an optimization problem is. In an optimization problem, there are many possible solutions and there is an objective function. The goal is to find a solution that maximizes or minimizes the objective function value. So in that case, there are two types of optimization problem: maximization problem and minimization problem. And when you find a solution, those type of solution is called an optimal solution. It is not called the optimal solution because there can be more than one solution with the same objective function value. And the main motivation for learning dynamic programming is how much improvement we gain by applying this technique. There are other types of algorithms for optimization problems that have exponential time complexity, exponential in the size of inputs. But if we use an algorithm that we design using dynamic programming, then we can design algorithm for the same optimization problems that has instead of exponential solution, it will have polynomial solution. In particular, I'll show one example where from exponential we will have an big of n square time complexity. So that's a huge improvement in time complexity from exponential to polynomial. Now, how do we know whether the given problem, if we have a problem, whether we can be solving using dynamic programming? There are two particular type of characteristics of problems that can be solved using dynamic programming. First one is optimal substructure and the second one is overlapping subproblems. Optimal substructure means if we have an optimal solution to a original problem and then we break into smaller subproblems of the same type, then in the original problems optimal solution, if we break into smaller subproblems, solutions for those, for smaller solutions, they will be themselves be optimal solutions to those subproblems. And it is another important property is those optimal like the smaller subproblems can be solved independently. If those smaller subproblems cannot be solved using independently, then dynamic programming is not a good choice for an algorithm. So if we have a problem that has optimal substructure, those type of problems can be solved by using dynamic programming by following three-step process. First step is we break the problem into smaller subproblems, and then we solve each of the subproblems by calling the function recursively. And third step is if we combine the solutions of the subproblems to create the solution of the original problem. And in case of optimization problem, how we do that? The third step, when maybe there can be many possible choices for breaking the original problem into smaller subproblems. We don't know which one will give us the optimal value, so we'll encounter each of the choices separately, calculate the function values for each of them, and then from those, for maximization problem, we take the maximum of all the possible choices for breaking into subproblems. In minimization, we take the minimum of all those subproblems. The function value or the objective function value, we take the minimum or maximum. In this way we solve the optimization problem. Now optimal substructure is also, if we have a problem with optimal substructure, there are another algorithm technique called divide and conquer. We can also be applying divide and conquer algorithm for those problems. One example is merge sort. In merge sort, we have an array of size n. We break it into size n by 2, like recursively called merge sort with size n by 2. Then from those solutions we create the solution of the original n length array. From those solutions we do some like shuffling or like rearranging of the elements, and then we get the solution for the whole array. But there is another, the second property that I mentioned about problems in for which we apply dynamic programming. The second property is overlapping subproblems. This is a big difference between divide and conquer algorithm and overlapping subproblems. In divide and conquer, we break the original problem into subproblems that are disjoint. For example, merge sort, we break into size n by 2. For each of those size n by 2 arrays, they are disjoint. But in case of problems where DP is best choice, those have overlapping subproblems. That means if we break the original problem into smaller subproblems and again break them into smaller subproblems, then there will be a lot of overlapping. And this is a good characteristic. This is an important characteristic for those type of problems. DP will give a very good solution. In this situation, if we apply the divide and conquer algorithm, then it will perform much more work than necessary. It will solve the same problems, same sub problems several times, so it will be wasting a lot of resources like time and space. So when we design algorithm, we have to think about space requirement and time requirement, especially very important. So if we have a problem that has overlapping subproblem, then dynamic programming technique is used in the following way. It will solve each subproblem just once and then save the result in a table. When a new subproblem we have a new subproblem, at first we will check whether there is already saved solution in the table. If there is a saved solution in the table, we use that value. We will not compute it again. Otherwise, we will call the recursive function call. Now, because it solves each sub problem just once and saves the result in a table, that means we can have polynomial time solution, and it will be the requirement that is needed for polynomial time solution is when the number of distinct sub problems involved is polynomial in the input size, and each such sub problem can be solved in polynomial time. Then the overall problem can be solved in polynomial time. Now there is a 4-step method for applying dynamic programming paradigm for algorithm design. At first we characterize the structure of an optimal solution. That means we study the problem and we see how to solve the problem. Then we recursively define the value of an optimal solution, and then we compute the value of an optimal solution from the smaller subproblem solution to the bigger problem. And the step 4 is this step 3 is we actually compute the value of the optimal the objective function, but we will be also be interested in how we get the optimal value, like the sequence of steps like broken and the solution. This will be more clear when we go for an example. So there are some examples of problems that can be solved by dynamic programming is rod cutting, that will go into detail, and longest common subsequence, optimal binary search tree, shortest path in graphs, and matrix chain multiplication. Now we'll go into detail for rod cutting problem. So we define the problem. We have an integer n, which is the length of the rod. We have a rod of length n inch, and then we have an array of integer p, where pi denotes the price of rod length I for each I from 1 to n. The problem is how we cut a steel rod of length n into pieces so that the revenue is maximized. That means if we break into several pieces and take the prices of those things and add those, what is the maximum possible revenue, and the output is maximum possible revenue Rn that can be obtained by cutting the rod and selling the pieces. It is also possible that if the optimal solution does not need any cut at all, the value of the full rod as it is, may be the optimal solution. That is also possible. Now we have an example. The first picture shows the length and the corresponding prices of rod of length I, and then we have in the second picture we have an example of rod cutting problem for rod of length 4. So the first solution, there are 8 possible cutting, the 8 possible ways we can cut a rod of length 4. The first one is no cut at all, so the length is 4 and the price is 9. For each of those pieces, the number on top of those pieces actually shows the price of that piece, and here we break at position 1. So we have length 1, price 1, and length 3, price 8. So the total revenue is 9. And we see that in this particular problem, the optimal solution is C, where we break into 2 pieces, each of price 5 and length 2, and the optimal solution is 5 plus 5 equals 10. Now, how many ways we can cut a rod of length n? For each distance I from 1 to n minus 1, there is the choice of we either cut or we do not cut. So there are 2 possible choices for each of the position from 1 to n minus 1. So there are 2 to the power n minus 1 possible ways we can cut a rod of length n. In the example, we have n is equal to 4, so we have 8 possible ways to cut. We use the notation for solution. A solution for rod cutting problem of a rod length n is denoted as a sequence I from I1 to up Ik, I1, I2 up to Ik, where k is a value from 1 to n, and that means we cut the rod of length n into k pieces of size I1 up to Ik. That means in this case, the corresponding revenue is the sum of the pieces Pi1 plus Pi2 plus up to Pik, which is the revenue possible. Now we go for a recursive formulation. We have an optimal substructure for this problem. For now you just assume that this property holds, but at the end of this lecture I will show that we have a way how to prove this property. Let Rn denote the value of the optimal solution for rod of length n, and the first possible choice is no cut at all. Then the price is Pn, and then we can consider at position 1 we can cut. Then we have 2 smaller sub problems. Rod of length 1 in the left side, that solution is recursively R1, and the rod of length n minus 1, the recursive solution will give us length Rn minus 1. In this way, in position R2 and position 2 and up to position Rn minus 1, we will consider all possible values and the possible revenue, and we take the maximum because it is a maximization problem. We can improve the recursive formulation. This one just shows the previous recursive formulation. We can improve the formulation by noting that we at each position I, we will consider that left part we will not break into pieces, and the right part will go for recursive formulation. In that case, for position I, the left part is the price is Pi for rod of length I, and for the right one we recursively call the function Rn minus I, and we take the sum, and then we take the maximum of all possible values of I from 1 to n minus 1, and that is the second improved recursive formulation. Because it has, like each of the choices, we break the original subproblem into one new subproblem, but in this formulation we broke original problem into 2 smaller subproblems in each choice. So in this way we have improved the solution, and as an algorithm designer we have to always think about how we can optimize in each step. We have to think about how we can improve the time complexity and space complexity. Now we have the recursive formulation. This is the formula for the recursive formulation, and this is the corresponding algorithm. This is the terminating condition for the recursion. When rod of length 0, we return 0. and otherwise we initialize this variable to minus infinity because we are going for a maximization problem. And here this formula is written in algorithmic notation, that is q and pi plus the recursive call for cut rod rake with n minus I, length n minus 1, and p is the array of prices, and finally we return this value. Now in order to learn about how the time complexity goes for this recursive algorithm, we study a structure called study a data structure called recursion tree. A recursion tree actually shows the recursive calls for a rod length of size n initial call and the relationships among the recursive calls. In recursion tree, each node level gives the size n of the corresponding subproblem, and h from a parent with label s to a child with label t means that the subproblem of size s actually have a recursive call to a subproblem of size t. And a path from root to a leaf corresponds to one of the 2 to the power n minus 1 ways of cutting up a rod of length n. In general, this recursion tree has 2 to the power n nodes and 2 to the power n minus 1 leaves. And the labels on the simple path from the root to a leaf gives the size of each remaining right hand piece before making each cut. So this actually gives us the solution. Not only the optimal value, from this recursion tree we can learn which position each and each of the recursive call how it was cut. So the child node with node when we have a parent node of size s and the child node of size t, that means the right subtree, right part of the recursive call has size t. That means the left part is a rod of length s minus t. In this way we construct the solution. And now here is an example for the given example. This is the recursion tree for size 4. So we see that for size 4 we actually need to consider each of the position from 1 to n minus 1. N is 4, 1 to size from the size 1 to 4 minus 1 or 1 to 3. That means it will also call recursive function actually terminating condition is for 0. That means it will also call size 0. So that means for size 4 there is an edge from size 4 to size 3 to 1 and 0, because it will size 4 rod cutting problem, it will call size 3, size 2, size 1 and 0. In this way we construct the whole recursion tree. And then we see there are lots of overlapping, like this size 0, this is called 8 times. This is a subtree of size 2. This one, sorry, not size 2, is size 1. This was called 4 times in the recursive function. And subtree of size 2, it was called 2 times. So we have overlapping subproblem, we already know that. So DP is a good solution. This indicates that dynamic programming is good technique for this problem. So now we'll go for the time complexity of the recursive algorithm. Let Tn denote the total number of calls made to cut rod the recursive function for a particular value of n. Then Tn equals the number of nodes in a subtree whose root is labeled n in the recursion tree. So for example, for size 3, how many subtree we have, and for size 4, how many subtrees is at that root with size 4. So for 0 there is just one call, there is no more extra call, so t0 is 1, and for tn the 1 is for the initial call itself, and then we call subtrees with size 0 to n minus 1. So we summation 0 to n minus 1 tj, that is the recurrence relation. The solution to this recurrence relation is tn is equal to 2 to the power n, and it is exponential. Now we go for dynamic programming solution. We know that for dynamic programming we will have a different table or array. So let R0 to n be a new array, and we initialize those to minus infinity because it is a maximization problem. Then we call the recursive function with size n, and this is the recursive function cut rod dp p and r. So at first we see this is the formula, recursive formula for ease of understanding. So first we say whenever we have encountered a problem, we see whether that value is stored in the table. If Rn is greater or equal to 0, because Rn was initialized to minus infinity, if it is greater or equal to 0, that means it is already solved. In that case we return the saved value. Otherwise we at first we have the terminating condition of the recursion. If n is equal to 0, then we return 0. Otherwise we go for computation using recursive calls. So initially initialize this variable to -infinity because it's a maximization problem, and then we have this formula pi plus cut rod dp p n minus I r. This is the recursive call, and then we take the maximum, and when we are done with all the calculation, then we save the value in position n, save in the table, and we return this value. Now for analyzing the runtime of dynamic programming solution, we will use a structure called subproblem graphs. Subproblem graph is a directed graph that contains one vertex for each distinct subproblem. The vertex labels give the size of the corresponding subproblem. There is a directed edge from vertex x to vertex y in this subproblem graph. If solving subproblem x requires a solution to subproblem y, or more easy way you can say that from vertex x to vertex y there is a directed edge. If the recursive call for size x makes a recursive call to size y. You can think of subproblem graph as a collapsed version of the recursion tree for the top-down recursive method, with all nodes for the same subproblem collapsed into a single vertex and all edges directed from a parent to child. So this was the recursion tree where we have all the recursive calls. But in case of subproblem graph, we see for subproblem of size 4, it actually depends on the recursive call. It makes a recursive call to 3, 2, 1 and 0. So there is a directed edge from 4 to 3, 4 to 2, 4 to 1 and 4 to 0. So all the size 2 they are combined into a single vertex. In this way we construct a, similarly for size 3 it actually makes recursive call to 2, 1 and 0. So there is a directed edge from 3 to 2, 3 to 1 and 3 to 0. In this way construct a subproblem graph. Now how do we calculate the time complexity? The subproblem graph is useful for determining the running time of the DP algorithm. We know that in DP algorithm each subproblem is solved just once, not more than once. So the total runtime of the DP algorithm is the sum of the times needed to solve each of the subproblem, and the total number of subproblems is equal to the number of vertices in the subproblem graph. And the time to compute a solution of a subproblem is proportional to the number of edges or the number of outgoing edges of the corresponding vertex in the subproblem graph. And because we know that in DP each problem is subproblem is just solved just once, so the running time of the DP algorithm is linear in the number of vertices, because number of vertices actually shows the number of distinct subproblems. And for each of the subproblem the runtime is proportional to the number of outgoing edges. That means the total runtime of the DP algorithm is linear in the number of edges of the subproblem graph. Now we'll go for the time complexity. So in this case the number of subproblems is the number of vertices in the subproblem graph. It is n plus 1 because there are size 0 to size 4 or size 0 to size n in the case of n. So the number of subproblems is n plus 1, and the time to compute subproblems on a vertex level j is the number of outgoing edges of the vertex level j in the subproblem graph. If we go for the subproblem graph, for 4 we have 4 edges, for size 3 we have 3 edges, outgoing edges. So for size n we have number of outgoing edges is n. That means for vertex label j, that means the subproblem with size j, the number of outgoing edges is j. Now the total time complexity is the total time needed to solve each of the all the subproblems. That means we run from 0 to n because there are like n plus 1 distinct subproblems, and time needed to solve subproblem at vertex level j, or the time needed to solve subproblem of size j. That means the number of outgoing edges of the vertex level j, that is j. So summation 0 to n j, and it is n into n plus 1 by 2 and big theta of n square. So we have polynomial time complexity. So from exponential time complexity we have come to a polynomial time complexity, and it is not, the power of n is not too much, it is just 2. So we have big theta of n square from big theta of 2 to the power n, which is a huge improvement. Now we go for bottom-up dynamic programming algorithm. Here we sort the subproblems by size and solve the smaller ones first. In this way, whenever you encounter a subproblem, whatever subproblems it will be calling, those are already solved. So there is no recursive calls. In this way, it improves in a great way from the top-down solution, because there is no recursive calls. Whenever we do recursive calls, we actually have to save all the local variables in stack and goes in this way. More recursive calls means stack begins in size, and there is no possibility of stack overflow if you go for this approach. This is the bottom-up algorithm. So similar, first part is similar. Then we go for a loop that runs from 1 to n for computing the value of Rj, that is the maximum possible revenue for rod of length j, and for each of those we initialize the variable to be minus infinity, and then we go in the top-down approach. Here there was r j minus y. Instead of here we actually used the recursive call, but here whenever we add position j or size j, we already know that all the subproblems that we will be calling, those are smaller than j. So for those of the values, it's already saved in the table, so we don't have to do the recursive call. We just retrieve the value from the saved table rj minus I, and then when we are done with position j, we save the value in position j at rj, and we return rn. Now the time complexity is easier to for this case, because it's much simpler notation, and the number of iterations of the outer for loop is n. It runs from 1 to n, and the number of iterations of the inner for loop is j, and the time needed to perform each iteration of the inner for loop is constant. And so we have two summation for the outer for loop and the inner for loop, and the time to perform the steps in the inner loop, it is constant. So overall we have big theta of n square. But if we compare the top down and the bottom up DP algorithm, the asymptotic costs of the top down DP algorithm and the bottom up DP algorithm are the same, big theta of n square, but the bottom up DP is practically much significantly more efficient than the top down DP algorithm, because there is no recursive calls and there is no stack that grows into size, and there is no possibility of stack overflow. Now we go for how we construct the solution. We already know the maximum possible revenue, but we would like to know how to cut the original rod of size n into pieces to get this revenue. So this is quite simple. I described that when we have this recursion tree, how we break into recursive calls, then we know the values of those how to break the original piece of rod length. So similarly we do this for without non-recursive way. Here is we have the extended cut rod DP bottom up. So initially we have another extra array s. Here we will actually say which location to cut. So similarly, because in the cut bottom up we have this maximum function, there is one simple equation, but now we will do more than one statement for so we go for an if then statement. So if q is less than pi plus rj minus I, that means this value will give us more possible revenue. So we adjust q to pi plus rj minus y, and whenever we adjust this, then we actually keep the position I, that this is the cutting position for an optimal solution in location j of this second array s. So sj actually denotes that for rod length j, the optimal solution will give when we cut the rod at position I. And then when we are done, similarly we save this value and we return both of the arrays. And for printing this solution, we initially cut the like extended cut rod TP bottom up, we call that, and then we start from position n while n is greater than 0. That means until we have any more pieces to cut. At position n, we print Sn. That means Sn means actually for rod length n, the optimal solution where we should cut the position. We did that means also the size of the first cut of the rod. So we print that, and then because we already cut that part, so we reduce the value of n by n minus Sn, because that part is already cut, and then we continue with the while loop. Now we will show how we prove property optimal substructure for a given problem. we can prove this. So the objective is that suppose we have an optimal solution for a problem which is created by solving smaller subproblems and combining the solutions of subproblems. Now we have to prove that the solutions to the subproblems used within the optimal solution of the original problem, they must be optimal solutions for those subproblems. It will be more clear if we go for an example like the rod cutting example. So the Corman textbook of Introduction to Algorithms, it has a proof of optimal substructure for the shortest path problem. Here I will show a proof of optimal substructure for the rod cutting problem in a similar way, and we can use the same proof idea for other problems with optimal substructure. Now the method of proof is proof by contradiction. So whatever we want to prove, we will actually assume the opposite of that, and then in course of the proof we will come to a contradiction, and then we can say that whatever we assume it is not true, it is false. That means we start with the opposite. Whatever we want to prove, we start with the opposite of that. Let I is equal to I1 up to Ik denote an optimal solution for rod length n. That means the optimal solution cuts the rod with lengths I1, I2 up to Ik. Then the maximum possible revenue for rod length n is Rn is equal to Pi1 plus Pi2 up to plus Pik, because Rn denotes the maximum possible revenue for rod length n. So that is the solution, optimal solution. Now let us consider the cut at length I1. It cuts the rod of length n into two parts, one with length I1 and one with length n minus I1. Now recall that the left part of the rod with length I1 is not further divided. That means we have another subproblem in the right side. The problem of length n is solved by solving one subproblem with rod length n minus I1. The left part we don't go into cutting again. So only we have one subproblem of size n minus I1. Now we have to prove that the original path sequence of cut is I1 up to Ik. We are already I1 is length this part is not broken into smaller pieces. Now we have from I2 to Ik. We have to prove that this sequence I2 up to I2 I3 up to Ik is an optimal solution for rod length n minus I1. Because we are proving by contradiction, so we assume that this sequence I2 I3 up to Ik is not an optimal solution for rod length n minus I1. That means there is an optimal solution J from J1 J2 up to JL for rod length n minus I1, which has revenue strictly greater than Rn minus Pi1. Because if this solution did not have revenue greater than Rn minus Pi1, that means this sequence of I2 up to Ik, that would be an optimal solution, but we assume that it is not an optimal solution. And if this value is equal to Rn minus Pi1, then that means I2 up to Ik would be another solution with price Rn minus Pi1. That means this optimal solution have revenue that must be greater than Rn minus Pi1. Now that means the maximum possible revenue for rod length n minus I1 is R sub n minus I1, the recursive formulation. Rn minus I1 is the sum of the rod lengths J1, J2 up to Pjl. That means it is the sum of Pj1 plus Pj2 plus up to Pjl, which is strictly greater than Rn minus Pi1. Now we use a cut and paste method as described in the textbook. In the optimal solution of the original problem I1 I2 up to Ik of rod length n, we cut I2 up to Ik and paste this different optimal solution we have for J1 up to JL for rod length n minus I1. So we have a different solution I1 J1 J2 up to JL. Then we say that this solution I1 J1 up to JL is an optimal solution for rod length n with revenue. This will be Pi1 plus Pj1 plus Pj2 plus up to Pjl. And this part from Pj1 to Pjl, this sum is greater than Rn minus Pi1. So the overall sum is greater than Pi1 plus Rn minus Pi1, which is greater than Rn. That means we have a solution with revenue greater than Rn. That means the solution I is equal to I1 up to Ik is not an optimal solution for rod length n, and we reach a contradiction. So thank you for your attention.